Hello, and welcome back. Day 22, 2021. Strap in, because this is going to be, this is kind of a wild one. Um, okay, so day 22, reactor reboot. Basically, imagine a big three-dimensional space where we have coordinates that refer to different little cubes in that space. Cubes can either be on or off. Um, and for our input, we get this, um, we get these lines. Each one specifies the coordinates of a box. So this first line here, this would be a box from the x coordinates 10 to 12, from the y coordinates 10 to 12, and the z coordinates 10 to 12, right? And we're turning on all of the points within that box. Um, And same for the second line, and then this third line, we are turning off all of the cubes in that third box. So the first step, we turn on a 3x3x3 cuboid consisting of 27 cubes. This makes sense. Here's the coordinates for all the points or cubes that we're turning on within there. Second step also turns on a 3x3x3 cuboid, but it overlaps. And so as a result, we're only turning on 19 additional cubes with the second line. Okay, and then the third step turns off a 3x3x3 cuboid that overlaps partially with some cubes, so it turns off 8. And then the final step turns on a single cube. And then after the last step, we can see that 39 cubes are on. So this is the basic idea. We just get a list of all these boxes, and we go through, we turn some cubes on, or we turn some cubes off, depending. And then the question at the end is how many cubes are on? And actually, part one of this is a little more restrictive. So it says within the ranges -50 to 50 on the x, y, and z axis, how many are on? And then for part two, it's just how many are on within the entire space. So a couple ways you could think of to solve this. First of all, you could just, why not just initialize a giant array, rank 3, you know, just the minimum x coordinate, minimum y coordinate, minimum z coordinate to the maximum coordinates. And then we'll just go through and we'll put, for each one of them, we'll calculate some ranges. We'll set all of the points in there to 0 or 1 depending. And the problem is that some of these ranges are extraordinarily large. And so first of all, you're going to have a space problem keeping track of all this stuff, and then you're going to have a time complexity problem because you have to iterate through these entire ranges to set all of those bits, either 0 or 1, right? Or on or off or whatever. Okay, so that's probably not feasible to do, and in fact, that's I believe this advent of code is set up like this a lot. The reason problem one is restricted to this range is because that approach is actually feasible if we're just doing a 100 by 100 by 100 cube of possible answers, right? You could actually just construct that and then go through and iterate and set all the points one by one. For part two, it's not feasible because we have these incredibly wide ranges, right? Okay, so how about we just calculate the volume of all the cubes? It's just, width times height times length. And we can just add all those up. Well, the problem is that they intersect. And so if two cubes intersect, and let's say that they both have volume 27, you can't just say, okay, 27 plus 27, 54 total volume. If they intersect, then you have to subtract the intersection in the middle because you're counting it twice if you just add up the volumes. So that's possible. I am not great at computational geometry, so I don't really know the algorithms and stuff here very well. So I did some research. Seems like we have Overmars and Yap that came up with an algorithm in, what is this, 1991, somewhere in there. And they say they can find the union for a bunch of rectangular prisms in in dimensions over 2 log n in time. So for 3 dimensions, this would be n 3 over 2 log n, right? Um, so I was looking at this. This looks cool. It uses this, apparently it uses this thing called an orthogonal partition tree, which I'm probably not going to build. So yeah, looks cool. Not going to do it. Um, these folks came up with the volume of a union of cubes, which doesn't necessarily apply to our problem because our boxes aren't necessarily cubes. Um, but this is an improvement in 4 over 3 log n. And, I looked in here for some ideas, and this is all horrendously complex, at least for me. Okay, and then, I looked at the Reddit thread of the solutions, because, it's been like 8 months or whatever. There are some great solutions in there. A lot of them are based off of this thing called the inclusion-exclusion principle. So basically, if you're calculating the union of the points in 2 boxes, um, it's the size of all the boxes minus all the intersections between them, and then plus some more intersections. Basically, you can think of the volume of a box is its volume, so length times width times height, minus all the spots where it intersects with other cubes. And so people came up with these recursive solutions where for each one, you determine the intersection with all the cubes that have been previously placed. Those intersecting cubes can themselves intersect, so then you need to recursively determine the volume of all of those intersections. Very elegant solutions. I didn't think it was like super array based, so I wanted to come up with something a little more suited to APL. Obviously, you can do recursive solutions and things like that in APL, but um, I wanted something more array based, and so I came up with something, and that's what I'm going to be showing you today. It gets pretty interesting, so let's dive in. We're going to be working with the test input, specifically this test input here. I'm leaving off these final 2 lines because they're outside of this neg 50 plus 50 range. And basically we're going to be solving this problem backwards. I'm going to do part 2 first, and then I'll show you how we can filter our answer down to just this. But for now, we'll just include these lines, so we're only counting points within that range, so we can check our work here. Okay, so this is our input. As usual, we can do in get test. We get a bunch of rows. Close this. And we can assign this to P. And then we want to pull out all of the digits. So we can say for each P, partition is the line in, we want to include the negative sign and then all of the digit characters, like so. That gives us all the digits. For each one of those, we can execute turning them into numbers. And then what I'm going to do is I'm going to reshape them into a 3x2 matrix, and then we'll mix them all together. So this gives us a rank 3 array, 20 by 3 by 2, where each submatrix here contains a set of start and end points. The top row is x coordinates, middle is y, bottom is z. So for example, this first matrix here defines a box that starts at neg 20x plus 26x, neg 36 plus 17y, neg 47 plus 7z. So we will be using this, so we'll assign it to m. for, I don't know, matrix, I guess. Okay, and then the other significant piece of information from our input is these beginning off and on keywords. Really, we can just look at the second character of each line. If it's an in as in off, or sorry, if it's an in as in on, then we know that it's on. If it's an F or basically not equal to N, then we know that it's off. So we can just say for each P, we'll do in equals index 2. Oh no, there we go. Okay, so these are all of our on or off designations, and we can just assign this to S for signs, I guess. Okay, so that's our input parsed out. We have everything that we need. How do we actually want to solve this? So I was looking at, these different things that I was showing you. Nothing seemed good. Then I came up with, or I didn't come up with it, but I was reading, and I happened upon this idea of coordinate compression. And the idea is that we can't just instantiate a giant rank 3 array and flip bits, because the ranges are huge, so the size of the array would be extremely large, and we would have to iterate through a bunch of points for each row in order to actually set those bits. But not all of those points are actually going to change. So we can look at, why don't I just show you? Let's see. So I want a list of all of the start and end coordinates for the X, Y, and Z axes. Okay. So we start with M. We can do a dyadic transpose on M. I talked about dyadic transpose a little bit in my last video. What's the shape of M? So basically I want that 20 on the ends. I want the 3 in the lead, and then 2 is fine. Wait a minute. Hang on. There we go. Okay. And then, so these are all of our X, Y, and Z coordinates split out into submatrices. And then we can say catenate rank 2 to put them all into lists. We're basically just catenating the different matrices. And then if we look at the shape of this, 3 by 40. If we look at the shape of M, it's 20 by 3 by 2. So they have the same number of elements. They're just, it's just shaped differently. And then I'm going to say rank 1, sort them. So each row we're sorting from least to greatest, right? And then I'm going to call this, we have to do one other thing, which is I'm going to increase the end coordinates of M by 1. And it'll become apparent why I'm doing this here in a minute. So we can do this, and we'll call this C for coordinates. Now, what was the point of doing this? Well, so we can't just create a giant rank 3 array and start twiddling bits in there, but if we could compress that array somehow so that we're only setting meaningful points, then maybe we can compress it enough where that approach actually becomes feasible. So if we look at C, and if I break this apart, so that we have enclosed lists of all the different axes. And then I concatenate reduce. This should give me a list of indices or points in a rank 3 array. It does, great, in a 40 by 40 by 40 array. And then let's say that I use stencil to take a 2 by 2 by 2 slice. And we're just going to look at the enclosed slices. And then I'm just interested in the fifth one. I think this should be a decent explanation. Okay, so this giant array, you can think of uh, think of our coordinates here. We have a list of x coordinates that includes the start and end points for each box. It's now sorted. Same for the y-axis, same for z. And then if you think of a rank 3 array with those elements lined up along each axis, then when we flip on any point within that array, we are basically, rather than just saying that a particular point is on, we're saying that a particular cube is on. So for example, in this case, let's, if we, in this array, if we flip on um, the fifth point from the left on the x-axis, the fifth point from the left on the y-axis, fifth point from the left on the z-axis, these are this is the value at that point, and then these are the values directly succeeding it on each one of the x, y, and z axes. So we can see here that what this point actually signifies is it's a cube starting at neg 46, continuing until neg 41, right? This is the difference on the x-axis. And then we can say on the y-axis, this is different from neg 32 to neg 29. And then on the z-axis, it's the difference between neg 47 and neg 38. And basically, because we've put together all of the start and end points for our cubes, we know that we're like the points in between these coordinates are never going to be set individually. They'll only be set as part of turning on or off a particular cube in our input. So if we get to so we can parse our input and we can think about what coordinates we want to set in this matrix that we're building. Rather than setting individual points, we are setting on or on these subcubes that we've subdivided our space into. And if, for example, we had a 1 at this 5 by 5 by 5 coordinate, well, neg 46 to 41 is 5, neg 32 to 29 is 3, so 3 times 5 is 15. And then neg 47 to neg 38 is 9, right? Pretty sure it is. And then 9 times 15 is, what is that, 135? So we could say that a point at, if this is turned on, then we've turned on this sort of rectangular prism that we defined that has a volume of 135. Hopefully that makes sense. I think it'll make a little more sense as we go on, as you see what I'm building here. But this is the general idea, and then the reason that we do this is that the shape of this matrix that we built is 40 by 40 by 40, rather than rather than a potentially much larger matrix or potentially much larger array, depending on the ranges that we have in our input. Like you can imagine if we had an input that went from negative 100,000 to positive 100,000, then at least one of our axes, if we do it the naive way, is going to have to be 200,000 units long. And that's just, it's not going to fit in memory very well. It's going to take forever to set the bits within it, et cetera, et cetera. But compressing them so that we're operating on a much smaller array, now it becomes feasible to do, right? Okay, so we have C, we have our coordinates for the X, Y, and Z axes. We are going to need our, we need our matrix, but everything starts at 0. So what's the size of our input? It's 20. We can take 2 times because we have start and end elements. And then we'll subtract 1 because, oh, not times, -1 plus. We'll subtract 1 because in this matrix, or in this array that we're building, the last element is never going to be set. So basically the size of a cube is determined by the difference between the point that we're setting in the matrix or in the array and the succeeding points on each one of the axes. So the last point on each one of the axes is not going to be set because there's no succeeding point to bound it, to give it any sort of size. So for this particular problem input, we're going to have a rank 39. We're going to have a rank 3 array that's 39 by 39 by 39, and they all start as zeros. So the shape of this is, again, 39 by 39 by 39, but this is our original array. We're going to set this to D for digits, I guess. Naming things is hard. Okay. So how do we, so now that we have our coordinates that sort of tell us what the points in this array that we've built mean. We have the array itself, which is much smaller than it would be if we tried to solve this naively. Now basically we just have to iterate through our input and calculate the different points that we have to set in this array and actually do that setting. So m is our input. If we transpose m, the way that we would, so if we look at the transpose of m and we look at C, we basically want to figure out what indices in C each one of these lists would fit into for the X, Y, and Z axes. And C is sorted. We sorted the rows. So one of the better ways you can do this is by using binary search, right? So you could say, tell me the index of -20 in the x-axis list. You can start in the middle, and then if that element is greater than your target, you can move towards the lower range. Otherwise, you can move to the upper range, et cetera, et cetera. Presumably, that's how binary search works. And I don't want to implement binary search myself in APL, but luckily there's a primitive that does it, and that's just interval index, right? Interval index, given a sorted left side, will tell you where the indices of everything on the right side are. So if we have the transpose of M, and we can say for each matrix, rank 2, for each row, rank 1, interval index on C. And this, now all of these numbers, rather than being absolute start and end points, are instead indices into our coordinate array. And now if we transpose M back, we get it, it's the same shape as the input. But now, rather than setting, if we look at this and then we look at M, rather than going through and setting points between -20 and 26, between -36 and 17, between -47 and 7, now we've compressed the range. So we're setting points between 19 and 31, between 3 and 24, between 5 and 25. And the ranges on those differences are much smaller. So we have less iteration that we have to do in order to set these points. Um, so now we can say for each matrix, which represents a particular box, well, actually we have a problem here, which is that if we're gonna do iteration, we need some way to generate these ranges, right? So we're gonna say from 19 to 31, from 3 to 24, from 5 to 25. Turn some cubes on. But we need to actually generate these indices because APL doesn't really have a way to say like, okay, index from here to here. So how do we do that? We'll need to create a function. So like, let's say that we wanted to generate ranges from 2 to 5. Probably the first thing you want to do is take the difference. So the difference is 3, right? But if we want to do 2 to 5 inclusive, then we're actually trying to get 4 elements. So 2, 3, 4, and 5. So we want to do 1 plus. Okay, that gives us 4. And then we can take iota, and we can take the minimum of our 2 elements and add that. 3, 4, 5, 6, this is close, but now we just need to subtract 1. So this train right here is giving us the inclusive range from the left side to, from the left argument to the right argument. So we'll call this R for range. And now, if we, again, this is our input indexed into our sorted coordinates, our sorted start endpoints. Now we can say R reduce, and we're iterating between each one of these points. So like we had 19 to 31, right? And now this is 19 to 31 inclusive. We had 3 to 24, and now it's 3 to 24 inclusive, right? You with me? I told you this is going to be a wild ride. Okay, so now the shape of this is 20 by 3. The shape of our input, or at least the matrix that we're using, is 20 by 3 by 2. So each of the rows in here represents a particular box. So we can say rank 1. Rank 1, we can split this part, and we can say x, y, and z is our row. So we've assigned variable names to the different axes here. And then we can say D for all the x points, for all the y points, for all the z points. I want you to assign something. And that something is going to be the signs that we pulled earlier from our input. And then we can say rank 0, 1. So for each element in the signs array, and for each row in this in these set of coordinate ranges that we've calculated, you run this function, and in the rank 3 array that we created earlier, that we initialized, we're going to be setting the coordinate ranges to whatever the sign is. So the sign is 1 if we're turning cubes on. That makes sense. The sign is 0 if we're turning cubes off. Easy enough. Okay, so that ran, presumably, and we would expect to see changes in D. Now, if we just look at D, we're going to see a bunch of zeros. But if we ravel it and add together, we get we can see that we've turned on 36,045 of our little subcubes. Unfortunately, that is not the answer that we get here. And the reason is that, remember, we're not counting points, we're counting subcubes, which means that those subcubes don't necessarily have an area of just 1, they could have an area of more than 1. right? Or actually an area of 0. So how do we calculate the areas? Well, we have our coordinates, and initially I was thinking about like, well, actually, so we can find the pairwise difference of successive elements in C with a windowed reduction, and this is just absolute value minus. So this tells us for each pair of elements, it tells us um, how far the next element is from it. And if we look at the shape of this is now 3 rows of 39. If we look at the shape of D, it's 39, 39, 39. So with the windowed reduction, we lost an element in C because we're looking at pairwise elements. What we can do is we can break apart this into the X, Y, and Z elements, and then we can say outer product times reduce, like so. And what this is doing is it's saying, okay, we're going to construct a rank 3 array. Each coordinate in that array is going to be equal to the multiplication of the pairwise difference of all of our coordinates, right? So if we had like a negative 49, negative 47x, then that point is going to be 2 for x. And then if it was like negative 30, negative 27 for y, it's going to be 3 for y, right? So we find those differences, we multiply them all down, and then this tells you the area of each of the cubes in our little submatrix. So we can assign this to A for area, I guess. Maybe volume would be better, but whatever. And now the shape of A is 39, 39, 39. The shape of D is 39, 39, 39. So we can take A times D, right? Because in D, the cubes that we care about have a 1. The cubes that we don't care about have a 0. So we can just multiply together. We found the area of all the cubes in A, but the ones that are turned off will be multiplied by 0, so they won't appear in the final tally. And then we can just ravel it and sum, and we get 590,784, which is our answer here. Now, so yeah. What all did we do? Basically, we sorted all of the start and end points for each axis. And those then become the bounds for a new compressed array. And when we set points or turn off points within that array, we're not just turning on and off individual points, we're turning on and off cuboids, right? And then we go through our input and we turn on or off all of the cuboids depending on the index within the sorted start and end points, right? And then we calculate the area of all of the cuboids, multiply it times the area that we've been building, so that when a particular cuboid is on, meaning it's switched on with 1, we multiply that by the area. If it's off, it's 0 times, so that's always going to be 0. And then we just enlist everything and add it up, and that tells us our total volume. So it's basically like the naive algorithm where we're just going through an array and we're just flipping on or off cells. But rather than having a potentially extraordinarily large array, we've compressed it down to these little subcuboids that we then can calculate the volume of. So if we put it together, 22 video.dialog, what does this actually look like? So let's see, we had a lot of stuff going on here. Right. So we're creating our matrix. Excuse me. And then we calculated the signs. Then we created our sorted coordinate array. Then we created our zeroed out matrix that we're, or not matrix, but array that we're going to be modifying. And then we have our range function that will calculate inclusive ranges from the left argument to the right argument. And then we actually do the iteration. So we are doing a transpose. We're finding the coordinates. We're transforming our input from absolute values to relative values using interval index to find the coordinates. And then we're modifying our rank 3 array, just iterating through and setting or turning off cubes. And then we are generating all of the volumes for all of our cubes. And then it's a simple matter of multiplying the volume times our mask of cubes and then adding them up. And I think that's correct. So if I run all of this, I get the correct answer of 590,784. Now, I sort of cheated a little bit because remember that in our test input, I left off the final two rows because they are outside of the range. So if I add those now and I run this again, I'm going to get a much larger answer because I've included some very large ranges. We actually get some floating point thing here, so it's important to turn on print precision to 34 here so that we can actually, so we get all the significant digits. This is a very large number, obviously. How do we filter to just elements within this -50 to 50 range? Well, we have our list of coordinates here. It's all sorted, and basically we can say, okay, so we want -50 must be less than, and 50 must be greater than or equal. And this gives us a Boolean mask, which we can then, same sort of construction that we've been using, we can then generate a rank 3 Boolean array, just anding together these masks. We'll call this F for filter. And then all you have to do is, rather than just area times D, we take F and D. Oh, right. For the coordinates, we want to drop the last element in each row. Because again, the last element in the coordinates doesn't matter. That will never be set to 1 because there's no successive bound there. So yeah. Right. Neg1 drop F. Now I can do F times F and D, and this gives us, I'm basically using F as a filter or a mask to only keep elements of D which are within that -50 to 50 range. Then you can do A times ravel plus reduce, and you get the same answer as before, 590,784, even though we have elements outside of that -50 to 50 range. So if I add this, now we can say this here is our answer to part 1 because we're filtering to that range. And then if we don't filter to the range and we just have everything, then that's going to be part 2. And this is the complete solution. So now comes the big challenge. If we look at our actual input, it is massive. So we have 420 cuboids that we're calculating, and some of these ranges are crazy, right? The naive approach would never work here, but because we're compressing, now it becomes feasible to do, theoretically. Let's see if it actually works out. So I'm just going to replace this with 22.txt, and if I run all of this, it's taking quite a bit of time to calculate. It's chugging through it. Okay, so for part 1, we got 620, 241. That is indeed the answer for part 1. And then for part 2, we get this large number, 128456. Yeah, this looks correct. 128456, last 3 are 324. Yeah. So, I mean, it took some time to calculate, a few seconds, but it's nothing crazy. There were a lot more efficient solutions that were posted that ran in the sub-second range. But this is fairly concise, and I think it's interesting because it shows this technique, coordinate compression, that I've never really had cause to use before. Now check this out. The size, so this this area rank 3 array stores the volume of each one of our cuboids, right? That is an 839 by 839 by 839 array. And the size of that in memory is 333. So it's just under 5 gigs. So the default workspace size when you're using Ride and when you're using Dyalog is, I think, 1 gigabyte. So if you want to follow along and do this at home, you need like at least 16 gigs of memory, and you need to set the max workspace size to something like 12 or above. And then the size of D, which remember, is just our Boolean array where we're keeping track of whether we turn cubes on or off, is much smaller because Dyalog does this thing called, I forget what they call it. It's like bit bashing or bit compression or something. Basically, they don't have to use a whole byte to store a Boolean value. They instead use the actual bits. So the size of D is instead just like 73 megs. So that's a lot more reasonable. But basically, we've generated these like massive arrays, and then we just chug through them using parallel operations. And the time complexity of all this is atrocious, but runs in a couple seconds. It's not the most efficient solution, but I think it's pretty cool, and it's fairly concise. We're at 10 lines here. Some of these could probably be, you could like, I do this sometimes if I'm just using maximum line length, etc., etc. Yeah. Anyway, so that's our complete solution. Takes a little bit to run, but I think it shows some interesting array-based techniques, computational geometry techniques as well. The coordinate compression stuff is cool, and we got the opportunity to use, lots of rank operators, lots of transposes. We're basically keeping things in large contiguous arrays as much as possible, which is the reason why, despite the horrendous computational complexity of this solution, we're able to return things in a relatively short amount of time. Cool. Well, that's the video. Hopefully all of that made sense. But I thought this solution was sort of interesting, and I got pretty excited about it. So, anyway, thanks for watching.